So whenever you tell me, I'm going to start.
Right. Well, I mean, it's a pleasure to have Professor Bilionis from Purdue here with us. He obtained his PhD in applied math from Cornell in 2013. He has been at the Mathematics and Computer Science Division at the Oregon National Lab. And then in 2014, he became the assistant professor of mechanical engineering at Purdue in the USA, where he established the Predictive Science Laboratory. That, well, I mean, he will tell us about what they are doing here in a moment. The mission of PSL is to create artificial intelligence technology that accelerate the pace of engineering innovations. The applications range between technical system to socio-technical system. His research is highly interdisciplinary and has been funded by NSF, NASA, DARPA, and several industrial grants like Cummins, Eli Lilly, Ford, Facebook, etc. Professor Bilionis has published 55 journal papers, 2 book chapters, and 23 conference papers. So it's our pleasure to have you with us, and the virtual space is yours right now. Okay, I will ask everybody to switch off the mic and the cameras, and I will do it with mine right now. Thank you.
All right. So thank you for the invitation. It's a great honor to tell you guys about what we're doing in my lab. So without further ado, I'm going to start. I'll tell you 3 things basically of increasing complexity. First, I'm going to give you a high-level view of what we do in my lab. Then I'm going to tell you about the project we have with NASA on extraterrestrial habitats. And then we're going to pick one of the topics that are relevant to this project, and we're going to get really deep into it. So increasing complexity, as I said, when we get to the end, we may start skipping slides if it's getting very late and you guys are getting drowsy. So let's see. So first I'm going to tell you about my lab. These are my students, the postdocs. These are the guys and girls who do all the work. I'm just going to present to you what they have done so far. Our mission is to create artificial intelligence that accelerates the pace of engineering innovation. I'll tell you what I mean by that with examples. Our philosophy is this: probability plus physics or causal relationships. We use probability to quantify uncertainty. We use physics to capture causal relationships between things. And by physics, I mean PDEs, ODEs, or even just structural equations that you think should hold. Machine learning. So we're using state-of-the-art machine learning to basically put everything together. If there are functions that we need to learn, we represent them with neural networks or Gaussian processes or polynomial Gaussian functions or so on. This is where machine learning is coming. If we have to train these functions using data, we use machine learning approaches. And they will become apparent what I mean by that when we get to the last part of the talk. And the 4th ingredient is real application data. So I started as a mathematician. I just used to do toy examples where everything worked. I now work on problems where nothing works. So I'm going to tell you a few of the things that are really, really, really hard. And then we're going, at the end of the day, see some toy examples again. But I'm trying to get more and more into the real applications, into messy data, where out-of-the-box techniques do not just work. All right, so the current applications that we have in my lab, and I would say the 5 most important ones are combustion engines funded by Cummins. I cannot tell you about this because it's an export control item and is under a non-disclosure agreement. Hopefully much later, and if you come in the US, maybe we can talk about some of the things that are not protected. But it's physics-informed machine learning applied to combustion engines. We work on electric motors, design of electric motors, and quantifying uncertainties in electric motors with Ford. We also cannot talk about that. And we also work with Eli Lilly, which is a huge pharmaceutical and injectable biologics. So basically, modeling and designing the auto injectors, machines that allow you to inject biological nature drugs on your own. And all these projects are interdisciplinary projects. I collaborate with people who have domain expertise in relevant physics, with experimentalists that collect data, and I work in between trying to make these two communicate. There are two other projects that are very dear to my heart. One is high performance building, several projects funded by NSF. So basically making buildings more energy efficient by controlling the heating and cooling and other energy devouring attributes of buildings, and not just controlling the devices. It is part of it is controlling devices, but also controlling what the humans do. So how do you give incentives to the humans in order to achieve certain goals? And the project about which we're going to talk today, resilient extraterrestrial habitats. I'm going to tell you about this in a while. And that one is funded by NASA. So there are a few overarching basic research themes in my research. If you like the core problems that I'm interested in, let's go over them. High dimensional to quantification, sequential design of experiments, physics-informed machine learning, in the sense that you have, not just talking about physics-informed neural networks here, I'm talking about any approach that uses physics plus data to achieve something. Discovery of causal laws from data. So you see this is particularly important for the NASA application. Modeling humans as disturbances to engineering systems, and modeling humans as decision makers inside engineered systems. So imagine that in the extraterrestrial habitat, you may have a human engineer who makes decision, or an astronaut, whatever we're going to call them, I don't know, the people who live in these habitats. And then make decisions autonomously. How do you design a system that is resilient to such decisions? All right, we are mostly going to focus on the first part, high dimensional surface quantification, in the third part of the talk. And we are barely going to touch upon these themes to see where they fit in a specific project. Now, let me tell you a little bit about this project on extraterrestrial habitats and what it is about. And our vision is really to enable the design of smart and resilient space habitats. So habitats on the moon, habitats on Mars. And when we say habitats, we really mean research facilities. We're not going to build hotels on Mars, at least not yet. And our mission is not to design these habitats, but it is to create the technologies that you need in order to design these habitats, because you don't have on Earth the conditions of the moon or of Mars. You don't have the same atmosphere or lack of. You don't have the same type of moonquakes or Mars quakes. You don't have these extreme temperatures. You don't have this extreme radiation. You cannot really just go out and make habitats and expect them to work on the moon or on Mars. So you have to create the experimental facilities or the simulation capabilities in order to design the habitats. And that's what we do. We're making these experimental facilities. We're making these simulation capabilities. So this is what we do. So we make three things. One is we make a reference model of an extraterrestrial habitat. This is a physics-based model of the most important systems that you would find in an extraterrestrial habitat. The structure, of course, this is a detailed finite element model of the structure of a dome on Mars or on Moon that can be affected by moonquakes, it can be affected by radiation, can be affected by uh, micrometeorites hitting it and damaging it. We have a power system, a nuclear power generator modeled that generates power. We have batteries modeled. We have photovoltaic panels. We model the air inside the habitat with fluid mechanics and the heat transfer. We model the thermal management system that maintains the temperature. We model the pressure control. We model the oxygen generation. We model the exterior environment, of course, all the disturbances that affect the habitat. And also we model the robotic agents and the human agents that interact with the habitat systems, fixing and maintaining things. So that's one thing that we do, and that's what I have been mostly doing is making this model. The other thing that we're planning to do is make a cyber physical test. So we're basically going to take parts of this reference system and we're going to manufacture them. And in particular, we're going to manufacture the structure and the thermal management unit. And this is how it's going to look like when we're done. We have a huge room in Herrick Labs, the lab for smart buildings, and we're going to build inside there the dome. And the third thing that we do is make a coarse model of the habitat that will allow us to do design of habitats and study their resilience and also use it for real-time decision making and planning. Now, I lead, this is a huge institute. We have about 45 to 50 people engaged with it. There are at least 10 faculty members that are PIs, and I lead 1/3 of the institute, and that 1/3 is about situational awareness. So I'm going to tell you what situational awareness is. So situational awareness is about asking and answering two questions. First, where are we now? Where is the habitat now? So things like, are the ambient conditions safe, comfortable for the crew members? Is there dust on the solar panels? How much dust do we have there? Is there dust on the radiators that we need to send heat out? How much dust do we have? Is there damage on the structure? Where is it? What kind of damage? These are all fault detection diagnosis questions. That's how we call them, FDD for short. The second question you want to ask is, where are you going? So if you know where the habitat is now, can you predict where it's going to be in the future? What will happen to the ambient conditions, temperature, oxygen level, pressure, etc., if you shut down the thermal control for an hour? How much time do you have until you fix a structure leak? These are, answering these questions is called prognosis. So we work in the situational awareness thrust on fault detection diagnosis and prognosis mostly. I'll show you how it is implemented in our reference system. So each one of the systems that you see here has the capability to diagnose its health state. And it does it as follows. There are sensors. For example, the structure has accelerometers. And in particular, our approach uses the ambient vibrations to see what kind of excitation you measure on the accelerometers, and then you process them. You pass them essentially through a physics-based model of the structure, and you come up with an estimate of the stiffness of the various components of the structure. That's how we do the fault detection diagnostics. And then this information about the health state of the structure goes to the command and control, which can make decisions, and I'll tell you about them in a while. And it can make the decisions automatically or inform a human about this. So there's also elements of a human-machine interface. And I'll tell you in a while why you actually need the human there and I'll tell you right now, actually, you need the human because we cannot automate everything. That's why you need the human. All right, this is an example of how a fault detection diagnostics system works, the structure in particular. I'm gonna let this play and I'll explain what it is. This is work by Zizing Wang and Mohammad Reza, who are under the Awareness Trust. And so you see here a micrometeorite hitting the structure, and one of the segments of the structure is being damaged. And here you see that the system detects that segment number 2 was damaged, and then we dispatch some robotic agents that are repairing the structure, and the health state returns back to normal. So, and then you will see another case where the damage happens at a different location. But here, imagine you have two things essentially here. There is a reference system, a simulator that can be damaged by a micrometeorite and can be fixed. And that's a detailed finite element model on the background. That's one thing. And the other thing that you have here is a coarser model that is being used to do fault detection diagnostics. All right, so why is situational awareness needed? Why do you need to know where you are? Well, you need to know where you are so you can make, so if you're drifting outside the safe zone of operation, you can do something to bring your system back to the safe zone. So if you can imagine that, if this is the state space of the habitat in terms of performance, what do we mean safe, right? So if we have crew, is the crew safe? Do we have a temperature range that allows the crew to be comfortable and of course be alive? Do we have, are we within the right oxygen level range? Are we within the right pressure range? We have the right humidity. This is what we mean by safe zone. If something happens and you start drifting to the boundaries of the safe zone or even outside, you want to take an action that will correct your trajectory and bring you back to the safe zone. And this action is taken by the command and control based on the information provided by the fault detection diagnostics components. And in particular, our command and control can take two types of actions. One is it can change the set point of the mechanical systems, can go to the thermal management and change the temperature set point. Or it can send commands to the robotic agents or human agents to repair something. So if we detect that there is some damage on the paint of the radiator panels, we can actually send a robotic agent to fix that damage and then return the system to the nominal condition. And all these details are simulated. And this is an example of how this simulator looks like. There's a lot of complexity on the background. Imagine that this took, what you see here took 40 people 2 years to put together. So most of the things that are happening here, the detailed finite element models are on the background, you don't see them. Here, what you see is the fault detection diagnostic panels, right? So you see here detecting how much dust you have on the solar panels, the damage to the structure, dust on the radiators of the life support system, damage on the paint, and so on and so forth. And here you see basically some data being sent to the data repository. This is the communication network. Imagine that we are actually modeling the communication network. So the fact that you have sensors that send the data to a computational component that does the fault detection diagnostics, and that computational component sends the data through some routers to a data repository. This is explicitly modeled. And then the command and control, which is here on the bottom left, is just now, it's basically a terminal, looks at the data repository and the health state information and decides what action to take. And if it can fix something, it dispatches a robotic agent to fix that. So we're not done yet. We haven't reached yet the level of complexity that we would like to have in order to have something realistic and useful. So we want during the next year or so to increase the complexity so that we can enable research on unanticipated faults. So we want to have so many things happening so that we start seeing emerging behaviors. We start seeing the habitat being damaged in ways that we haven't anticipated before. And the reason we want to do that is so that we can then start doing the research that we actually want to do, which is on the real-time decision making and planning. Okay, we cannot do that research yet because we need something to control, and we have spent 2 years trying to make that happen. Probably going to spend one more year to get to the point where we have something truly complex that cannot be controlled by, let's say, standard reinforcement learning algorithms, for example. All right, so now we're going to start gradually getting into the third part of the talk, where I'm going to give you a little bit of technical details about physics-informed neural networks. First, let me tell you where exactly they fit within this picture. They are hidden, again, on the back end. So we need real-time physics-based fault detection, diagnosis, and prognosis. Okay, you need to be able to run your FDD systems in real time. And if you look at the details of the fault detection diagnostic problem, it is a filtering and calibration problem. So it is essentially a super hard inverse problem with PDE constraints, with physics constraints coming from partial differential equations. So it is ridiculously difficult to solve. In the case of the structure, imagine that you need to infer what is the stiffness at all the different components of your structure. So if you have more than 100 degrees of freedom, I would say if you have more than 10 degrees of freedom, good luck. It's actually a very hard problem. Okay, and we want to be able to go to hundreds or thousands of degrees of freedom. And this is, in order to be able to solve these types of problems, especially in real time, you need surrogates of the physical models with high dimensional inputs. So if you have a partial differential equation that depends on a few hundred of parameters or a few thousands of parameters, can you solve that equation for any given parameters super fast? And that's what we're going to talk about today. I'm going to zoom in into a very specific partial differential equation, the Poisson equation, and more general, an elliptic PDE, an elliptic partial differential equation. It's a very common equation in elasticity, magnetostatics, flow through porous media. So it's if you can solve that problem in high dimensions, you can likely have an impact in a wide range of applications. All right, so now we're getting to the third part, and I'm going to tell you specifically about solving high-dimensional stochastic partial differential equations. Now, we've done quite a bit of work on this topic. This is the paper that we're going to follow today. I'm basically going to take you through this paper. But we have also done quite a bit of work on the same problem with various approaches for high-dimensional uncertainty propagation. So let me tell you what it's all about. So imagine that you have a partial differential equation, this one right here. Okay, we're going to use this as an example, but you could have a source term if you wanted, and you can make it more complicated if you want to. It just has to remain elliptic. That's the constraint. But we're going to work with this equation with on a box with Dirichlet boundary conditions on the left and on the right, and normal boundary conditions on the top and bottom. And the thing that I want you to notice here is that this A of X, which is a field, is going to be an unknown parameter. So it could be any of the pictures that you see below. And what we want to do is we want to solve the PDE for all these pictures. We don't want to solve it for one picture or for two pictures. We want to create something, an algorithm that takes a picture and spits out the solution of the PDE at any location. Now, this is what we're going to do. We're going to use a neural network to represent the map from space, and let's call this picture conductivity, to the measure, the physical property u of x of xi. Okay. Now that xi, I'm going to use xi for the picture. Now that xi is a few thousand. It has a few thousand degrees of freedom. Okay. And I'm not going to, if you're familiar with the problem, I'm not going to follow the usual approach where you use Cardinal level expansion to reduce the dimensionality of the random field. I'm going to use the picture, and I want to build a surrogate model that works for any picture and for any realization from any random field. Okay, so let me tell you now what is the idea, and what is the idea for solving this kind of problem directly using the physical equations without any finite element solver. And the idea is to create a loss function, the minimization of which over the space of neural networks solves that PDE for all parameters. And here's the idea that you're going to find in the standard papers of Perdikaris, Pagnadakis, Maziaresi, Zabaras. And the idea goes back to a paper by Lagares in early 1998, if I remember correctly. And it has become possible over the past few years to routinely pose and solve these problems because of advances in automatic differentiation software like TensorFlow and PyTorch. But let's see what the basic idea is. It's very, 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 very easy to understand what it is. So you take your PDE and you move all the terms to one side, and then you square that and you integrate over space and time. And then if you're familiar with physics-informed neural networks, that's what you see in most of the papers, integrating over space and time the square residual of the PDE. And then the idea to treat parameters is to have an additional integration over all parameters. So here we have an integration over the pictures. We call it an expectation. And then you minimize what you get over the space of deep neural networks subject to the boundary conditions. So in our case, it looks like this. Okay. Now the first integral inside is over space. The expectation outside, I'm going to use E subscript psi to talk about this expectation, is over all the pictures. So you have here a number that you want to minimize. And if you minimize it, you basically solve the PDE, the strong form of PDE for all the pictures. If you get it to zero, that is, okay? And that's really nice. It's really straightforward, but it doesn't work. Now, if psi is 2, 3, 4-dimensional, it does work. If sometimes. If psi is high-dimensional, it doesn't work. Okay, and if you don't believe me, try it out. We spent quite a few years trying to make it work. And we had to sit back a little bit, think about it a little bit, about the problem a little bit, do a little bit of math, and come up with an alternative way to formulate the problem. So when it doesn't work, you do a little bit of theory. And here's what we did. We went full probability theoretic. We defined a general elliptic PDE. Looks like this. So this is the general form of the PDE you saw before. Now it has a source term. The only constraint is that A should be, the A that you see there, the conductivity, is elliptic. And then that omega there is basically an indication that everything could be uncertain. A could be uncertain, C could be uncertain, the source term could be uncertain. The Dirichlet boundary conditions could be uncertain. The Neumann boundary conditions could be uncertain. So we went here to this problem. And we asked this question: can we come up with a loss function for this problem, the minimization of which is probably the solution of the stochastic PDE? And the answer is yes, there is, and you can prove a theorem. And the theorem is similar to what you find the traditional work in stochastic finite elements, for which is not fancy anymore, but the work of Babushka, for example, but with some variations. But the proof is similar to what you find in proofs of similar theorems by Babushka. Anyway, the theorem says that if you have an elliptic operator and then you work in the right Sobolev space, then this loss function that you see here at the bottom has a unique minimum, and that unique minimum solves the PDE that you want for all pictures. That's what the theorem says. And if you notice, if you look at it carefully, it's not the integrated square residual of the PDE. It is essentially some sort of energy of the physical field, integrated, averaged over all randomness. And the nice thing that you notice here is that the natural boundary conditions, the normal boundary conditions, they just enter this loss function naturally, and that's why you call them natural boundary conditions, by the way, because they tend to do that. But the Dirichlet boundary conditions are something that you have to impose. All right, so I'm gonna skip over the sketch of the proof. I don't think we have time to go over it. And I'm gonna go over a practical implementation of this idea. And there are a few new elements. If you want to know about the proof, go into the paper. There are a few new elements here that I think are worth mentioning. So, of course, the randomness in this formulation is infinite dimensional. We cannot go anywhere with that. We have to discretize it. And if you want to be very careful about discretizing it, you can look at the recent work of Andrew Stewart at Caltech, some work by Karnadakis and even Perdikaris on what is the best way to do that without sacrificing a lot of accuracy. So that's one thing we're going to do. We're going to have to discretize the randomness or the field, the input field. We're going to enforce the Dirichlet boundary conditions with a neat trick. Natural boundary conditions are already in the loss. We don't have to care about them. And then we have to construct a stochastic gradient descent algorithm that converges. Okay, so let's do these things one by one. We find dimensional parameterization of the stochastic input. Basically, what we're going to do is we're just going to go from a field, from a random field, from a field to a picture. Okay, and we're not gonna care too much about how much error this introduces. This is not my job. If you want to know about that, go and look at the work of Andrew Stewart. The math for that are too hard for me. Okay. So the next question the thing that I'm going to do is we're going to enforce the Dirichlet boundary conditions, and we're going to do this with this trick. So we expand the solution in this way. There is a term here that satisfies the Dirichlet boundary conditions, and it's relatively straightforward to make this for simple problems. But even if your problem has an arbitrary geometry and arbitrary boundary conditions, you can still do it. And there's some work by Win and E that I can point you to if you are interested in doing this. And it's also cited in the paper. The second part is made out of two parts. This K there, which is 0 on the Dirichlet boundary conditions. And this is on purpose so that when K becomes 0, B which satisfies the boundary becomes active. And then the last part, this N hat, is basically a neural network that we're going to learn. So that's how we represent the solution. Okay. Now we'll go to stochastic gradient descent. And again, you may say, I have a nice loss function. Here it is. I can just go and do stochastic gradient descent on it. I can do Adams and it's just going to work. And if you try it, it's not going to work. Because you need to understand a little bit why stochastic gradient descent works. In this case, it's not quite the same as traditional training of neural networks where you have a bunch of data. So if you understand what are the theorems behind that make stochastic gradient descent tick, you can make this work. All right, so that's what the loss function we want to minimize, and we want to turn it. The trick here is to turn the integral into an expectation over some random variables that are chosen in a nice way. And we have to be careful to introduce the right normalization constants when we do that. That's a trick. Now, if you want to understand the details, again, I advise you go in and read the paper, because I'm giving in the paper some details that are not given in other papers. They're basically put under the rug. I'm explaining why this process will probably lead you to an algorithm that converges. And hopefully, if you pick up the process, you can apply it to different problems. So you see a bunch of things here. You see these special points that are independent, identically distributed, and uniformly on the special domain. This is a difference between this approach and the classic approaches on pins where the collocation points where you use to evaluate the loss are fixed. I'm basically telling you that they don't have to be fixed. As a matter of fact, they shouldn't be fixed if you want your algorithm to converge. The size, these are the pictures, should also be independent, identically distributed in the stochastic domain. So you sample random pictures. And there are some random points that you need on the boundary for the natural boundary conditions. All right, and then once you have this, you can do stochastic gradient descent. And if you have picked everything, as I showed you in the previous slide, there's a theorem, 1951, quite old theorem. It's called the Robbins-Monroe theorem. It guarantees that this algorithm will converge. Okay, stochastic gradient descent will converge. And stochastic gradient descent will converge independently of how many collocation points you use. You can just use one. So you can basically iterate with one sample in the spatial domain and one picture. And it's still going to converge. It may take forever because it's going to have a lot of variance, but it will still converge. All right, so let's look at some results. Now we're going to solve this problem with basically various random inputs for A and see how the approach works. And the first thing I want to show you, this will connect to those of you who are familiar with the elliptic, stochastic elliptic PDE problem and random fields. So on the what you see here on the x-axis is basically the length scale of a Gaussian random field. So the smaller the length scale, the more difficult the problem. So if you have solved this problem in the past, a length scale of 0.03 gives you very, very fine features in this picture, and it's an extremely hard problem to solve. Now, what I show you in these box plots is the L2 error, the relative L2 error in the solution of these stochastic PDEs when you use the standard approach for pins, the integrated square residual loss, and when you use the energy functional loss, which is what I just introduced a while ago. So what you observe here is that when you, and we're doing multiple research. So we train the networks multiple times. We do it like, I think here we do it 100 times. So 100 times we randomly start the network and we minimize the loss. And we get 1 point for the box plot of the corresponding box plot. What you observe here is that the integrated square loss not only has an error, a relative error, that is an order of magnitude larger, but it also has a bigger spread, meaning that if you run it 2 times, the results will be very, very different. And why does the energy functional loss work so much better in this particular case? It's because of the uniqueness theorem. Now, of course, the uniqueness theorem was on a Sobolev space. It wasn't on the space of neural networks. But if you make the neural network big enough, the solution up to some parameterizations of the neural network, permuting the internal neurons and all that, will be unique. And that's why it works better. So no matter where you start, you get to a very good solution. All right, these are some predictions from this network. The first column is basically the input. So you give it this picture, and it responds with a function of space. Okay, so you can evaluate it at any point in space, and you see the contour of the solution on the next 2 columns. In the middle column is the true solution computed by finite volumes. On the right, you see the predicted solution by the neural network. Now, the neural network was trained, and this particular neural network was trained with a wide array of pictures, and you can actually feed it random pictures that are not coming from the same random field. They can come from completely different random fields. So you see here at the top, we have a random field with a very small length scale, and on the bottom, we have a random field with a bigger length scale. And the network works well for both. Now, if you pay close attention, you will see that we're missing some fine features. You see there are some fine features in the solution that the network cannot capture. And back then when we wrote the paper, so imagine this is things, it was published in 2020, but we actually started doing this in 2017, and probably this result was something we have in 2019, because it took a year to publish. So you'll see, back then we didn't know why we weren't able to capture these fine scale features. Well, now we do know why we cannot. And it has to do with something called the spectral bias of neural networks. And this is something that came up last summer, spectral bias of neural networks. Basically telling you that neural networks first learn the low frequency features, and it takes them quite a bit of time to start learning the high frequency features. And you have to go to the network and change the initial layers you can go to the network and change the initial layers so that they can actually start learning the high frequency features immediately. And you introduce the so-called Fourier features at the beginning of the network. So if you go and do that, the results can actually become much better, but I'm just showing you here the results from the paper. All right, here's another example. So we fed it a channelized permeability and still performed adequately well. We fed it a sample from a non-Gaussian random field that you see on the bottom, and it did well. And as I said before, you can have one network for all types of fields, and it still predicts quite well. So here we compare the relative error you get from training a separate neural network for each one of the different types of random fields. So that's the blue. So the blue is you train a neural network specifically for a random field. The green is a neural network for all pictures. And you see, of course, you get a little bit of bigger error if you train for all pictures. This is expected, but it performs in terms of relative error quite well, less than 8% here. And if we had used the Fourier features, we didn't know about it, it will probably be a little bit better. And this is the extrapolated performance. So this pure extrapolation. What we did here is train a neural network on a Gaussian random field and in particular Gaussian random field with small length scales. And then we used it, and that's all I had seen. So I had only seen pictures from a Gaussian random field. And then we used this network to predict completely different random inputs from completely different random fields, even channelized fields which look like day and night. And the extrapolative capabilities were remarkable, I think, for the kind of training that we did. And this shows you that the network is actually learning how to solve the PDE. It's not just memorizing the inputs and outputs. Okay, so there are several remaining questions. The proof holds for a Hilbert space. How good is it for the neural networks? I don't have the capacity to study this problem. If you are mathematically inclined, be my guest. The solution is definitely not unique in the DNN space. In what sense is it unique? There are some open theoretical questions that I already mentioned during my talk. Okay, and I'm going to end with this slide, which is going to be a little bit more futuristic, just give you some hints of future research work that is worth doing. So the first is inverse problems in one shot, learning how to invert, exploiting this idea to solve an inverse problem, find the solution of an inverse problem as a function of data. So there is some work on that actually by Zabara's very recent work on invertible neural networks. I advise you to go and take a look at that. But the problem is not solved. They do inverse problems. I want to get into filtering and calibration problems, which brings the time domain, and it's a little bit more peculiar. Physics-based design optimization, high dimensions. There's a very nice, I don't know if you pay attention to this, but the CEO of NVIDIA last year in his keynote, he actually talked about physics-informed neural networks. And he showed an application of physics-informed neural networks for designing a heat sink. So they learned the physical response of a heat sink, velocity field, pressure field, temperature as a function of the geometry of the heat sink. And then they use that to do optimization. And they did it in 6 dimensions. There is a lot of potential here in higher dimensions, think topology optimization type of work. Completely open. Parsimonious deep neural networks for the solution of dynamical problems. This is a little bit esoteric. I'm not going to get into it. Probabilistic interpretation of physics-informed neural networks. This is something that I'm really fascinated with. But the math is extremely difficult. I still don't understand exactly what I mean when I write down the equations. And I have recently discovered that I need to learn, unfortunately, statistical field theory and quantum field theory to understand what I write. And then non-parametric learning of effective physics from data. There's quite a bit of work on that as well. It's very relevant also to the RedHi project to the resilient extraterrestrial habitat project when we start working on anticipated faults. So can you discover physical laws from data? And Stephen Atkins from GE, for example, has a very nice paper on that that I would suggest if you're interested in learning more about this. And with that, I'm done.
Thank you, Ilias, for a very nice presentation and challenging. We are open for a quick Q&A session. Please, if you have any questions, open your camera and introduce yourself. And go ahead, Americo, please. We have the first one.
Well, thank you, Alvaro. Professor Bilionis, nice presentation. I have 2 questions. First one regarding the fault detection problem. How to deal with false positives and false negatives in that kind of problem? For instance, isn't it possible to detect a nonlinear effect as a fault? If you're using a linear model, it can be blinded for this situation.
Yes. So obviously, and if you pay attention to the video here, This gives you the probability that you have damage on the segment. You see there are fluctuations, right? So you cannot trust this completely. You see what's happening here, so that you have the impact, and then you start detecting things that are not there. This is going to happen. So you need to, but because this needs to go to the habitat, you cannot make it super complicated, right? So you cannot go and use the more sophisticated Bayesian approach you want. It has to run on a super simple computer with very little memory. So the defense has to come on the higher level. So what do you do with this information? False positives are going to happen. You're going to have to make your decision making will have to take into account that. So here, in this particular example, for our decision making, we're waiting for a little bit. We're kind of averaging the probabilities. Basically, we have to, pick a window and make sure that something has been detected for quite a bit of time to act. And then when we act, we can still have a false positive. When we send here the agents to repair stuff, they don't start repairing immediately. First, they do an inspection, which in this particular case, it's simulated, so it's not happening. but in a real case, it will take pictures. The robots will take pictures, analyze the pictures, maybe send the data to a civil engineer. They'll look at them. We also have the ability to locally test the structure and go and hit with a hammer and listen to the accelerations and maybe locally solve a nonlinear problem. That's that's the approach that will go in the final application right now.
Put the safeguards in a following step. This is the idea.
Yes.
Okay. Yes. Second question regarding the loss function for the pin. You changed the perspective for a elliptic problem, change from the residual loss function to a energy inspired one. Is this true for other kind of problems when you use parabolic or hyperbolic equations, for instance?
Yeah, so that's an excellent
you
question.
can have a result that generalize this idea?
That's an excellent question. So it doesn't have an easy answer. So there is, first of all, the principle of least action, which is really the principle of stationary action. So you have a closed system that doesn't give energy to the environment or take energy from the environment. There is an energy principle for that. And even if it is evolving in time, there is an action principle, really. So there is a functional of the solution that you can minimize or find the stationary point of that works. So for closed systems, yes, the answer is yes, but it's not trivial. Okay, you have to find the action, and there's no minimum. It's a stationary, so it's weird. The answer for systems that have energy dissipation, friction, for example, is that when you need to augment the state of the system so that it becomes closed, then there is an action. So
move toward infinity.
There's
the dimension.
Yeah. Well, yeah.
Infinite dimension, every system is linear.
Exactly, yes.
Yeah, that's a very interesting question because, the energy norm is a natural norm for this kind of elliptical PDEs, which is not necessarily true for, let's say, as you're discussing,
so just to give you some examples
with elliptic problems.
Yeah, of course.
That's what I am asking.
For the Navier-Stokes equations, for example, there is an energy principle, even though there is energy dissipation. There is. For many elasticity problems that I work on, so on the Eli-Lilly problem, we do skin mechanics, and there are large deformations, viscoelasticity, and there are energy principles for those as well. Now, for arbitrary problems, you're going to have to come up with one. Or you can just try the square residuals. I'm just telling you they're not going to work as expected. But there's no, you cannot just write it down and expect it to work. It doesn't work like that.
Okay, thank you.
Is there any other questions?
Hi, I have a question.
Yeah, please, Fabio, go ahead.
Well, first of all, thank you for your presentation. It was a very nice presentation. I have basically two questions. One, if you ever consider to extend your formulation for transient case, for transient simulations, if you ever tried or if you ever tested, or if you ever try to use a specific topology of the neural network like reservoir computing or those that are specific for stochastic cases. Am I clear?
So the first question, yes, there are transient problems, and this relates to the first question, right? So are there energy principles? The answer is maybe there are. So for some transient problems, there may be energy principles, but most likely you're going to have to work to find one. And my guess is that it will pay off on the long run in terms of accuracy. And the second question, what was it about again? Can you please repeat it?
And the second question was concerned about the topology of the neural network. If you ever try to use a specific topology like reservoir computing to test your case, that's for.
Yes. So, all right. Again, if you just pick an N neural network, dense neural network with many layers, it's not going to work. I mean, I can guarantee you that. Pick a random problem, pick a loss function, try to minimize it to learn the physics, it's not working. So what we have found empirically is that you need, for sure, residual connections. These are connections that go directly from your input to your output and to the internal layers, bypassing the layers in between. There are theoretical reasons why these residual connections work, because they are essentially giving you an identity function that you are correcting. So you're learning the corrections to the identity. That's why the residual connections are good. And without residual connections, this doesn't work. And if you look carefully at most of the papers on the field, especially in high dimensions, they all have residual connections. Then when you, if you want to find the high frequency features, you have to introduce these Fourier features at the very beginning because of the spectral bias. And then this for sure if you want to find features. And then if you want to combine space and time, which will have fine variability, and the pictures, which are a little bit smoother, you have to you go to depot nets, which is a structure proposed by Kainadakis group to deal with this kind of fusion. But in general, even if you do that, it may still not work, okay, for your problem. So at the end of the day, you have to go to your problem, see if it's worth doing these techniques, and spend a couple of years to figure out how to do it. We are like a decade away from having a generic solution. But if you have specific questions, specific problems, I'll be happy to talk with you offline. Because I also have some notebooks that I can share with some examples.
It's a multi-phase, for example. Yeah, it's a multi-phaseful problem that you have different scales and different phases. That's discretizing, transient, and it's almost stochastic. So it's stochastic, but treated as average case. Well, we can talk about it later if you have time.
Okay. So I'm sorry, I have to run to another meeting.
Okay.
Right now has already started. I'll be happy to stay for more questions, but unfortunately I didn't leave a lot of time. If any of you wants to ask anything, feel free to send me directly an email, and I'll be happy to answer any questions. Okay. And I'll be happy to share the slides as well with you guys.
Yes, this is one thing I would like to ask you to share your slides. And if you need Ilia's email, just reach him at Purdue or send me a message. I have his email, no problem. Well, let's thank Ilia again for his time, and was a very nice talk.
Thank you all.
Thanks.
Thank you all. Thank you for the invitation. Bye-bye.
Very interesting. Bye-bye. Okay, I will stop recording. Just 1 second.